I'm just starting now. So the streaming has started. Okay. So we were looking at week 4 last session. So we'll continue with week 4 now. Okay.
Yes,
Right.
ma'am.
So in week 4, we saw what is span of a set. Span of, so if you are given with a set of vectors, span of that set of vectors is nothing but the all possible linear combinations from the given set of vectors. Okay. And we also saw that span of S is a vector subspace. Okay. And we have seen that. So suppose if you are taking one single vector, span of S is simply here, the line y is equal to minus x, right? So here span of S is the set of all vectors x comma minus x such that x is in R. Okay. So this is the set we saw last time. Okay. And then we saw that. Okay, so these are some things we already saw. Can you answer it now? Span of any non-zero vector in R2 is? What is the answer? What is the answer for this? Span of any non-zero vector in R2. So we just even saw an example here. So we took a non-zero vector from R2 and we saw what is the span. So can you tell now what is the span of any non-zero vector in R2?
Normal line.
Yeah. So it is a line passing through origin.
Origin. How is it necessary to always pass through origin?
See, all the time span means it contains a zero vector. So yes, it will pass through the origin. Okay. Mainly we are considering vector spaces with usual addition and scalar multiplication. So if the addition and scalar multiplication are defined differently, then instead of origin, it will pass through the identity vector, additive identity. Okay. So for now, yeah. So it will pass through the origin. Okay. Span of any non-zero vector in R3. What about in R3 again? In R3 also,
So
you are considering only one vector. So what is the span of one vector?
normal line. Again, a line
Line.
passing through
It is
origin.
again a line. It's again a line passing through origin. Right? Okay.
Yes.
What about the next one? So if you have two vectors in R2, okay, so and that they are linearly independent. So what is the span of S?
What's the basis of that vector?
The entire R2.
Yes. So it is the entire R2 itself. Okay. So it is the entire space. Okay. Fine. What about the next one? So if S is U1, V1, W1, U2, V2, W2. So now you have two linearly independent vectors from R3. So what is the span of S?
Plane in R3.
Yes, you are correct. It is a plane in R3 and it passes through
Origin.
right? Okay. And look at the next one. So you have S is equal to U1. You have now three linearly independent vectors from R3. So what is the span of R3?
Entire R3.
Yes, we have entire R3. Okay, fine. So we saw what is a spanning set. So if you have a vector space and a subset S of V such that span of S is V, then we call this set S as the spanning set of the vector space V. Okay, fine. Now what is the basis of a vector space? A basis B of a vector space V is a linearly independent set that also spans V. It means what? Every basis is also a
Spanning set.
yes, spanning set, and it is also linearly independent. Okay, fine. And we saw some equivalent conditions for basis. So we saw that the equivalent conditions are we can either say B is maximal linearly independent set or B is a minimal spanning set, right? So typically for Rn, so what is the typical example for a basis for Rn?
1001 for R2
Yeah.
and uh,
1,
So
0,
the
0,
standard order
and
basis we say, right?
yeah.
Okay. Okay, fine. So any n linearly independent vectors in Rn forms a
basis.
basis. Basis, right? Because we know that already it is linearly independent and the span of n linearly independent vectors in Rn is Rn itself. So it forms a basis.
Ma'am, I have a doubt.
Yeah.
So this is okay,
Mm.
but what if we have matrices? So can we flatten the matrices and then check for the basis?
That is not necessary if you understand how to do it directly. So to find the so I have included several examples today of how to find basis for matrix spaces. So during that time, if you have doubts, shall we discuss that again?
Yes,
Okay.
yes, yes. Okay, ma'am.
Okay, fine. Okay, so and then we saw what is the dimension of a vector space. The dimension of a vector space V is the size or cardinality of a basis B of V. It is denoted by dimension of V. Okay, so the number of elements in the basis is nothing but the dimension of the vector space V. Okay, any basis for Rn has exactly how many elements?
N elements.
N elements. And what is the dimension of Rn?
N.
N. Okay,
And
and we saw this example also. So here you have a set of three vectors. So now this is a spanning set for W, correct?
Yes, ma'am.
So now you have S, and you know that span of S is equal to W. Now what is the dimension of W? How will you find?
Two. Two, ma'am.
Yes, we have already seen that. In this case, it is very obvious that these two are linearly independent vectors, or if you take any two vectors, they are linearly independent. So you see that W is spanned by two linearly independent vectors. So the dimension here is 2. Okay. So in general, what is the dimension of any line passing through origin in R2?
One.
Yes. And what is the dimension of any line passing through origin in R3?
One.
Yes.
1,
What is the dimension of any plane passing through origin in R3? 2. What is the dimension of Mn of R? What is Mn of R? Do you remember the set of all
Yeah.
n by n
Matrix.
square matrices?
matrices. Yes.
So what is the dimension of Mn of R?
N square.
Yeah,
Uh,
n square, right? Because for
square.
example, if
Hmm.
you consider M2 of R, if you remember, we saw already a basis for this, which was 1 0 0 0 0 1 0 0 and then 0 0 1 0
1 0
and
0
then
0 1.
0 0 0 1. So we have already seen this basis for M2 of R, and you see that there are two square elements here. So the number of elements here are 2 square, right? So in general for Mn of R, you know that you have n squared. What about the set of all rectangular matrices? Suppose you are considering all m by n matrices with real entries, then what happens?
M into N.
Then I'm into N.
The dimension is
M cross N.
m
M
times
cross N.
of
Yes.
n, right? Okay. Okay, fine. Okay, so if V is span of S, where S is a linearly independent set, what is the dimension of V? You can answer in terms of S.
So the cardinality of S is the
Yes,
dimension.
yes. So dimension of V is the cardinality of S. So this symbol, kind of the hash symbol, we use to denote the cardinality of a set.
Okay.
Okay. Okay, so this is the cardinality.
But this notation hash symbol is not a general thing. This is you introducing it like that.
Sometimes some people use like modulus symbol, sometimes people use, but
And also,
it may be confusing to use modulus sometimes. So I'm using this. So it's just a symbol. Yeah.
okay.
Ma'am, we can write
Ma'am,
n of s.
Yes,
uh,
n of s is also fine. The final
that,
point is dimension here is cardinality of s. Yeah.
ma'am, that rank and dimension is same, right?
We have not yet started with what is rank. We are going to cover what is rank. That time I will answer this question. Okay.
Okay, okay.
Fine.
Thank you.
No need for any new symbols. Avoid confusion. Okay. Here I made some spelling mistake. I guess cardinality. Okay. Can there be a linearly independent set in a vector space V whose size is greater than the dimension of
No.
V? Yes.
No.
No.
No, it's
No,
not
ma'am.
possible.
Correct. Very good. So I guess at least some of you understood the concept clearly. So up to this, what are the concepts in week 4 you should know clearly? You already have seen in week 3 what are linearly dependent and independent sets. Now in week 4, you know what is mean by span and what is mean by basis, what is a spanning set, and what is dimension. So these things must be very clear to you now. Okay, so now we are going to see how to obtain basis from a spanning set. See, here we had a spanning set, right? We had a spanning set and finding a basis was not at all a difficult task. Straight away we were able to find. But in many cases, it need not be straightforward like that. Okay, so we have two methods here. So write down the vectors as rows of a matrix. Apply row reduction on A to obtain the row echelon form. Okay, so first we are going to write these vectors, whatever is given as rows, and then we are going to apply row reduction on A. Okay, to convert it into row echelon form. Then the non-zero rows of the reduced matrix forms a basis for W. Okay, and the number of non-zero rows in the reduced matrix is the dimension of the subspace. Okay, so whatever steps is given here, let's do it. So here you are having a subspace spanned by these three vectors. So we are going to find a basis for this. So you see straight away, maybe some of you are able to figure out, but it's not very straightforward like this one, right? So we are going to adopt this method we just saw. Okay, so what is the first step now?
Form a matrix.
Yes, we form the matrix A. So we write A as 1, 1,
1, 1,
2,
2,
2,
2, minus 1, 4,
minus 1, 4, and then 3,
3, 0.
0, 6.
306.
Okay. So the next step is that we are going to apply row reduction. Okay. So now we are going to apply row reduction and convert it into row echelon form. Okay. So now how do you convert this into row echelon form? What is the operation we can do? For the last row, first tell me for the row 3. For
1,
Go 1 by
3 times row 1, row 3 minus 3 times row 1.
row 3 minus 3 times of row 1. All right. So you will have 1, 1, 2, 2 minus 1, 4. And then here this becomes 0. And what happens to this entry here?
Minus 3,
Minus 3. And then
1. Oh, sorry, this is 6, 0.
0, ma'am.
0,
0.
right?
Ma'am,
Okay.
row 3 is the addition of row 1 and row 2. So it will get 0, 0, 0 if we do that.
Yeah, see, row reduction can be done in any method. Yes, whatever you are saying, yeah, maybe that also is one way to do it. So for row reduction, everyone can do it in a different way. Okay, so yes, what you're saying is correct. Okay, so what can be the next step? Can anyone tell?
And similar for row 2 also. Row 2
Yeah,
Ma'am,
row
R2 minus 2 R1.
times R1.
R2 we can replace with R2 minus 2R1. So in that
Yes,
way,
ma'am.
what is that you are getting? 0.
0, and,
Here what?
minus 3,
minus
minus 3.
Minus 3.
Minus 3 and then 0. Right?
0.
Yeah. So now here we can write R3 as R3 minus R2. So you have 1, 1, 2, 0 minus 3, 0, 0, 0, 0. And then obviously you can divide Second row with what number?
-2.
minus 3.
So you have 0, 1, 0, 0, 0, 0. So now is this in REF form?
Yes, ma'am.
Yes,
REF.
ma'am.
Yes,
So
ma'am.
you
Yes,
have
ma'am.
obtained the REF form. Now, what is that given to you? You obtain the REF form, and what is the step 3? The non-zero rows of the reduced matrix form a basis for W. So what are the non-zero rows?
The first two rows.
Yeah.
The first,
So
first,
step 3,
first and second.
yeah. So B is equal to 1, 1, 2, 0, 1, 0. So this forms a basis for W.
Ma'am,
Yeah.
one thing about this.
Yeah.
So REF is not unique and basis is also not unique. But RREF is unique. So what that form? Standard basis.
No, see, yes, you can say in that way, some kind of standard basis. We usually say standard basis for the whole spaces, not for subspaces. But yeah, what you're saying is to some extent matching. Yeah, RREF kind of gives you the standard basis for whole spaces. Yeah, you
Hmm.
get 1 0 0 0 1 0, so you get all ones and zeros in most of the cases, but not in all cases.
Hmm. But that will be unique. That basis is unique.
When you're considering maybe let us say you are considering a n by n matrix with all linearly independent rows, in that case you will end up with a standard order basis, but
Hmm.
otherwise we cannot guarantee that. Okay,
Okay.
fine. Okay, so now this forms a basis. So what is the dimension of W you observe?
2.
Yeah.
2, ma'am.
Okay, so what is the drawback of this method? In this method, the basis vectors may be different from the vectors in the spanning set. So we are not getting the same vectors from the spanning set. Instead, we are ending up with some different set of vectors. So we have method 2, which is much preferable. So almost the same steps we are going to do, but we are getting vectors from the same set. So let's better do method 2. So it's not wrong if you do method 1. The only thing is that if you want vectors from the spanning set itself, then we are going to use method 2. It's exactly the same, very similar, except that here we are going to consider the vectors as columns. Okay. So step 1. So your A is now 1, 1, 2, 2, minus 1, 4, 3, 0, 6. Okay, so you are going to find the row echelon form. So step 2, you are going to find the row echelon form. So what is the first operation we can do here again?
Ma'am, R2 minus R1.
Ma'am, R2,
First you should start with R3 usually.
R3 minus 2 R.
R3 minus 2 R2 R1.
Okay, so 1, 2, 3, 1 minus 1, 0, 0, 0, 0, right? And then what is the next step?
R1 minus R2.
R
R1.
Yes.
R2 is R1 minus R2 minus R1.
R1
So you get 0 minus,
minus 3.
yeah. And the next step, you get R is equal to 1, 2, 3, 0, 1, 1, 0, 0, 0. Okay, so here we have done R2 is 1 by minus 3 times of R2. Okay, so we have got the row echelon form. Now the columns of A corresponding to the columns of R containing pivots form basis for the column space of A. So now what are the pivot elements? So this is a pivot element.
Yes, ma'am.
This is a pivot element.
Yes,
Yes,
ma'am.
ma'am.
So
Yes,
now
ma'am.
what we are going to do, so the columns of A corresponding to the columns of R containing pivot element. So what are the corresponding columns here in A? First, second, right? So the first and second column forms the basis for the given set. So now here you can see that what are the first two columns? 1, 1, 2, and 2 minus 1, 4. So now this will form a basis for W.
Ma'am,
Yeah.
one thing. So if there are these are three vectors,
Mm.
so if we can remove any one of these and say that this can be written as a linear combination of other,
That
so
is
why?
not the case always, right? If all three are linearly independent, then what will you do?
Yeah, that is one thing. Let's say two are independent and one is dependent. So
So
then,
how do you find whether they are dependent or independent?
yeah, that thing I am also saying that we can write like any one of them as the linear combination of the
You
other two.
can try it out, but if it fails, then you are going to stack up there and then you are going to start with this process again, right?
Yeah.
So either you can go to this method, you can sometimes observe direct relations, or you straight away do this quickly. Or the other way, because you have three vectors from R3, can anyone tell what is the simplest way to identify whether they are linearly independent or
Determinant.
not? Yes.
Finding the
Find
determinant of this.
Determinant.
you find the determinant. With
Finding
the
the determinant.
determinant, you know that the
And
determinant is sorry, the set is not linearly independent. Okay,
Uh,
in that set, you have less than three. The basis cannot have three entries definitely. So it is going to be less than three. Again, be careful. Sometimes it can be one as well. Only one element can be there in the basis. You have to be careful that there are not multiples. So just blindly when the determinant is zero, don't write any random two elements. Make sure that there are no multiples inside. Okay,
yeah.
fine.
One.
Yeah.
Also, like I have no doubt about this. Like why I should choose this method, but I have doubt why this method works. Like we in this method we say that this first and second vector are independent, and the third vector is dependent on these two. But
Yes.
can we write the first vector as a linear combination of second and third?
See, that is always possible when you are able to write. If there are given three vectors, if you are able to write one of them as a linear combination of the other, obviously, then you can write any other vector as a linear combination of the other two. So this is just a specific method to give you what are the two vectors. Sometimes if you have like multiples, then it will leave out the multiples and going to give you only the first vector or something like that. So it is just a specific way of doing, that's all.
So yeah, that is like a confusing to me why this works. It's like I how this decides that these two are independent and the third one is dependent. So we
See,
can.
here, see, that is what I'm saying. If you are choosing the other two, also, it might still work. So, that is also the case. Here, I'm saying this is one possible answer. It is not saying that this is the only possible answer. Because obviously, you see that these two are not multiples. So, the rank is, sorry, no, we have not yet started with rank. You have two linearly independent vectors here. So, you can choose actually any two from this. But this is a straightforward method. You have like a specific way to find these two vectors. That's all, to avoid any confusion. Okay.
Okay, ma'am.
Yeah. All right. So now we have seen how to find basis from a spanning set. Suppose you are not given the spanning set at all. You are just given what is the subspace W alone. In that case, how do you find the basis? Let us start with a very simple exercise, a simple example. So let us see from R2. So for R2, what are the non-trivial subspaces? Do you remember? The trivial
100.
subspace for any spaces, first of all, are the zero space and the whole space itself. So for R2, apart from the trivial space, what are the other subspaces?
Uh,
Line
any
passing through
coordinates
origin.
of
X.
any line which is passing through
Yes.
origin.
So any line passing through origin is an example, right? So you take this particular W. For example, suppose if I am taking W is equal to set of all x comma y such that x plus 3y is equal to 0, right? How do you find a basis for this set? This space, how do you find a basis? So x comma y Now how can I rewrite y using the given equation?
minus x by
Minus
3.
Minus
minus
x by
x.
3.
Minus x by 3.
Minus x by
X by
3,
3.
right? Minus x by 3. So x is equal to minus 3y. So you have, oh sorry, I wrote it the other way around, right? Y is equal to 3y is equal to minus x. So y is equal to minus x by 3, right? So you have x comma y is equal to x comma minus x by 3. So now if you take x commonly, what is the vector you are having?
1
1
minus 1
comma
by 3.
minus 1 by 3.
So you can say that basis for W is 1 comma minus 1 by 3. So if you want to avoid fractions, or if you want, if suppose you are given like 4 options out of which you have to choose, how do you identify? Suppose
We
this is
can
not the vector given. How do you identify, match it with this?
3 comma
um
minus 1.
we can check for the multiples of this vector.
Yes,
Any scalar which, yeah,
yes.
yes.
So if so, any scalar multiple of this vector, any non-zero scalar multiple of this vector will also form a basis, right? Okay, fine. Okay, so now let's move on to R3. So in R3, so if you are given with only a plane passing through origin, you know that the equation is given by set of all x comma y comma z, ax plus by plus cz equal to 0. Okay, so now for this scenario, how are we going to find a basis? So let us consider a specific example where you have this equation 2x plus 3y minus z is equal to 0. So for this, either you can make the z as 0, okay, and then you have 2x plus 3y. You can randomly put some value for x, and then you find the value of y. Similarly, you set another variable as 0, and choose some random variable, random number for x, and find the value of z. So this is one way of doing. The method 2 is very similar to what we did for R2. For R2, what we did, we just simply took out the variable and we found the vector. The same way we can do here. So we rewrite the given equation. This is the given equation in this way. Z is equal to 2x plus 3y. Now the plane can be rewritten as x comma y comma 2x plus 3y. Okay. So now we take out x and y commonly. So if I take x outside, so here you have an x, here there is no x, so 0. Here you have 2. Plus, when you take y, in the first place there is no y, so 0. Second place 1y, third place 3y. So you have now got two vectors. So any vector in this set W is a linear combination of this vector and this vector. So you can say that they form a basis. So if you call this as V1 and this as V2, then V1 and V2 forms the basis for W. So is this method clear? Both the method clear for finding the basis for a given subspace, which is
Ma'am, first method is not very clear. Like,
first method.
yeah, yes, ma'am. First method, I didn't understood this.
See, for first method, what we are doing, we are making first, we are nullifying one of the variables. So we are making one of the variables 0. So either you can make x0, y0 or z0. Traditionally, first we are making z is equal to 0. Okay. So once z is 0, now you have only two variables. So if you have two variables, if you know the value of one variable, you can find the value of other variable, right? So we are randomly giving a value for the first variable and finding the second variable. The same you are doing for the since you know that this is the equation of a plane, you know that you need two vectors in the basis. So we are done with the first vector. So to find the second vector, again we are making another variable here as 0, and then again giving a random variable for random number for one of the variables. Here we put x is equal to 1 and find the other variable. So you got the second vector also. So you know that now this forms a basis. Okay.
In 3D, it is like we are choosing a point in a 3D space and then like trying to see a plane.
See, we are just trying to find two linearly independent vectors from this plane. That's all. Okay. Here your z coordinate is 0. Here your y coordinate is 0. So they are going to be linearly independent. That's all.
Okay, then.
Okay.
Yes, yes.
Yeah.
Ma'am, method one, we are considering Z as independent variable.
Z as?
We are considering Z as independent variable.
Z as infinite.
Independent variable.
I am not saying dependent or independent here. Here we are just taking z as 0. You can in fact take x as 0, y as 0. That is up to you. That's not a problem at all here. Okay, you can choose any one of the variable as 0 and do the same thing. It will work. Okay, fine. But
Ma'am,
method 2 may be easier. Yeah,
can you please explain the method too?
method 2. Yeah. See, in method 2, in this case, here you see that z is equal, you have no coefficients for z. So I am taking z is equal to 2x plus 3y. Sometimes there are coefficients for all the variables. So in that case, you have to take z is equal to, for example, the coefficient here is minus 5, suppose, let us say. Then what you have to do, z is equal to 1 by 5 times of 2x plus 3y, you will write. Okay. So here the case is very simple. You simply write z is equal to 2x plus 3y. Okay.
Ma'am, we have to take always Z, or we can X or Y also.
Anything you can take. That's what I'm
Any
saying. Here
variable.
the scenario here is the coefficient of z
It's
is,
easy. Yeah,
yeah,
it's
that is why
comfortable.
I'm choosing in this way. Otherwise, you can choose any other variable also.
Got it, ma'am.
Okay. So maybe I can do one example. Suppose I'm having something like this: x plus 3y minus 2z is equal to 0. Then it's better if I choose x is equal to 2z minus 3y, right?
Yes,
In
ma'am.
this way, I can write the set w as set of all 2z minus 3y, comma y minus z, where my y and z are varying in r. Now, what are the vectors here? If I am taking y commonly, what is the first vector? Can you tell? What is the coefficient of y in the first coordinate?
Minus 3, ma'am.
Minus
Second
3.
coordinate?
1
1.
0.
0. Right? And then what are the coefficients for z?
And two
2
2,
0
2,
0.
0,
0,
1.
1.
1.
Okay. So you see that now these are the basis vectors. Okay. So these and this will be basis vectors for this space W. Okay. So it does not matter how you are picking. So even in this case also you can choose 2z equal to x plus 3y. This is also fine. And then you write as z is equal to 1 by 2 x plus 3y and then do. That is also fine. See, basis is not unique. So there are multiple ways of finding basis for a given problem. Okay. So it depends on what your options are also. So if you are given an MCQ or MSQ, then you have to look at the options and you have to think accordingly. Okay.
Okay, ma'am.
Okay,
Fine.
ma'am.
Even by calculating either way, our the calculated vectors will always be linearly independent.
Yes, this way of calculating, yes, it is always linearly independent only. Okay.
Mm.
Yeah.
Ma'am, can the basis of a vector space have lesser vectors than the dimension?
Sorry, what?
Uh, can the basis of a vector space have lesser vectors than the dimension?
See, the definition itself is that, so the dimension of W should be the same as the number of elements in the basis. So here W is a plane, so the basis should definitely have two vectors.
Okay, but then the subspace of it can have lesser vectors.
Yeah, then in that case, yeah, so for a subspace, you have to look at the dimension of the subspace, not the dimension of the space. So now if you are considering W, now W is a subspace of R3, you look at the dimension of W. So W is a plane and the dimension is 2, for a plane. So you need two vectors in the basis. Okay? Clear? All right. Okay, so there is another type of subspace which you can see in R3. So something like this you may have. So W is the set of all x comma y comma z in R3. Okay, where you are given with more than one equation. Okay, so in this case, the solution completely depends on the solutions of this system of equations. So you have to solve this system of equation to understand what is the required basis. Okay, so for example, I have taken this particular scenario. So for this scenario, you are having x plus y minus z is equal to 0. And then you are having 2x plus y plus 3z is equal to 0. Okay. So now the first equation, let me call this equation number 1. This is equation number 2. So the first equation, from that I can write z is equal to x plus y. Is that correct? Yeah.
Yes.
Yes, ma'am.
So now I am going to put this z is equal to x plus y here. So 2x plus y plus 3 times of x plus y is 0, which gives us 2x plus 3x, which is 5x. Shall I write directly?
Yes.
Yes,
5,
ma'am. Of course.
So you have 5x plus
4y,
4y equal to 0. So from this, what you can say, y is equal to minus,
5x by 4.
yeah. So from this now, you know that z is equal to x plus y and y is equal to minus 5x by 4. So what can you say about x then, z then? X minus 5x by 4, which is, what's the answer?
Minus x by 4.
Minus if I 4.
Minus x by 4, right? So your w reduces to x comma, for y you write minus
And the
5x by 4,
5.
and for z you write minus
Minus x by 4.
x in R, right? So this is nothing but set of all x times of 1 minus 5 by 4 minus 1 by 4 x in R. So you can in fact say that this is span of this particular vector. Is it, tell me whether what I'm writing is correct or not? Is this correct?
Yes, ma'am.
Yes, ma'am.
Right? So and this vector forms a basis for W, correct?
Yes, ma'am.
Okay. So now I guess finding basis for subspaces of R2 and R3 is clear to you, right? So these are the most general type. Maybe sometimes you have some other types also, but I have given the technique for the most general subspaces we are using. Okay, fine. For Euclidean spaces. By the way, are you familiar with the term Euclidean spaces? What are Euclidean spaces?
Yes, sir.
What
Yes,
are
ma'am.
Euclidean
No, ma'am.
spaces?
R
In general, we refer
R,
to Rn
R,
as Euclidean spaces. Okay, so Rn as Euclidean spaces and other I refer to these as matrix spaces. Okay, so for I have given some methods of finding basis for Euclidean spaces. Next we will see for matrix spaces. Okay, so for matrix spaces, so here you have a problem where you have to choose the correct option. So the first one, what is the dimension of the vector space M1 by 2 of R? It is given as 2. Is that correct?
Yes.
Yes.
2R.
Yes, ma'am.
What is the dimension of the vector space M2 by 1 of R?
2.
Is this correct?
No, ma'am.
No,
No.
ma'am.
Should be 2, right?
Hmm.
The dimension of the vector space M3 by 3 of R is 3.
9.
It's not correct.
Yeah,
Nine.
it should
3.
be
It's
9, right?
3 square 9.
Okay, a basis of M2 by 2 of R is the set given by this. Is this correct?
True. Yes.
Yes, ma'am. True.
Yes.
Okay. So in general, how do we find dimension or basis for a matrix space? That is the next thing we are going to see. I guess here are some specific examples given to you. So diagonal, scalar, symmetric, upper triangular, lower triangular. Okay. So let us maybe start with the V1 here. If we don't have space, we can use the previous space. So if here, what is V1? We are asked to find the basis for the following set. So V1 here is the set of all symmetric matrices. Okay, here symmetric matrix means recall that A transpose is equal to A. Okay, so V1 consists of set of all matrices A, B, C, D. Now, what is the transpose of this matrix? Can you tell?
ACBD.
Okay, A, C, B, D. Now it is given that this is equal to A, B, C, D, right? A transpose is equal to A, right? Right? So now if you compare these two, what is that you get?
B is equal to C.
Yeah, you get B is equal to C and anything else? That's all, right? Okay.
Yes, ma'am.
So it means you can rewrite V1 as set of all A, B, B,
B, D.
D, where A, B, and D are real numbers. Okay. So now how many variables you have here?
3.
3.
3.
So means what is
3.
the dimension of V1?
3.
3.
3.
And how are we going to find the basis?
Uh, we find the linear combination.
Just like we did for the plane passing through origin. So
Uh,
take A times this plus B times a matrix plus D times a matrix. You will get 3 matrices which will form a basis. So now can you tell what is the first matrix?
1,
1 0
0,
0
0,
0 0
0, 0.
Yeah. Second one,
0 1 1 0
0, 1, 1, 0.
third one.
0 0 0 1.
0, 0, 1.
Okay. So what is the basis for V1? So basis for
3.
V1 is given by these 3 vectors. So let us call this as A1, A2, A3. So this will form a basis. Correct? Okay.
Yes,
yes.
ma'am.
So is this clear to
Yes,
everyone?
ma'am. Yes,
Okay.
ma'am.
Yes, ma'am.
Okay. So now the second one. Do you remember what are scalar matrices?
Yes, ma'am. Diagonal matrix in which diagonal
This
are same.
diagonal entries are same.
Yeah.
Diagonal elements.
So the remaining
They
entries are?
remain.
0.
0.
Yeah. So you have V2 is the set of all, let us say alpha 0 0 alpha, alpha in R. Now can you say what is the dimension of V2?
1.
1.
Okay. So what can be a basis for V2?
Identity matrix.
Yeah.
C times identity. Uh,
Okay. Fine. Okay. What is V3 now?
okay, okay, yes. Span
It's
and
a
okay.
diagonal matrix. Okay. So we can write A0 0 B, AB in R. So what can be the dimension for V3?
2.
2.
2.
2.
2.
And what can be a basis for V3?
2.
0, 0, 0.
Yeah. What is the basis? I'm asking. Dimension is 2. 1 0 0
1, 0, 0, 0, and
0, 0,
0,
0, 0, 1.
0, 0, 1.
Yeah. Okay. Fine. Okay. What about V4? The set of all upper triangular matrices. So you have V4 is A, B, 0,
0 D.
C. So you have A, B, C varying in R. So now what is the dimension of V4?
3.
3.
3. And what can be a
3.
basis for V4?
3.
Don't say 3 for that basis.
One, ma'am, 1
1
0
1
0
0
1
0
0
0
0
0.
0 0 1 0
0
0
1
0
1
1
0
0
0 0 1.
0 0
0
0
0 0
1.
1.
Okay. So I will leave V5 for you to work out. So V5, you do it as a homework. Okay. Simple only, right? You can do, right? Okay.
Yes, ma'am.
What is
For V5 is nothing but the set of all lower triangle 2 by 2
low?
lower triangular matrix.
Okay.
All right. Okay.
Okay, ma'am.
Okay. So before this, maybe I'll ask you one thing. So can you say that whether the set of all 2 by 2 matrices whose determinant is 0, is this a subspace?
Subspace of what?
Subspace
No.
of the M2 by 2 of R?
Yes. Uh, um, yes, it
No,
is.
because determinant is 0, then it will be linearly dependent. And we want a
Yeah.
linearly independent set of columns.
See, my question, understand my question. My question is that suppose I'm saying, so let's say S is equal to set of all matrices in M2 of R such that determinant of A is 0.
Hmm. Yeah,
I'm asking if
it
this
is.
is a subspace. Is this a subspace of R, M2 of R?
Yes,
Yes.
Yes.
yes,
Okay,
it is.
so for subspace, what are the two conditions you will check?
Scale.
Closure under multiplication and addition.
And zero zero
Multiplication, addition,
should
and
be
0
there.
vector.
Okay, so I am taking two random matrices from this set. So does this matrix belong to this set?
Yes,
Yes, ma'am.
Yes.
Yes, ma'am.
Yes, ma'am.
Does this matrix belong to this set?
Yes.
Yes, ma'am.
Yes, ma'am.
Does this matrix belong to the set?
No.
No, ma'am.
Then how
Oh,
are you saying that this is a subspace?
mm,
Right?
yes.
So the answer is no here, right? You have to be careful while answering. Okay, let
Yeah.
me ask another question. Okay. So let suppose you have say A is equal to set of all matrices here such that the trace of A is 0. Now what can you say? Is this a subspace?
I think no. Because
Maybe
trace is
yes,
the sum.
because the diagonals is
Yes, ma'am.
0. Diagonals will be 0.
No, 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 no.
No matter whatever the other values are.
Trace is the sum of diagonal elements.
Sum of diagonals. Yeah.
Yes. Yes.
Some maybe some negative element for
So
one
suppose
matrix.
you take A1 and A2 are two entries from S2. You know the trace of A1 is 0. You know the trace of A2 is 0. Right? Now what is trace of A1 plus A2?
It's also
Trace of
0.
E1 plus
It is also 0, right?
It
Similarly,
can.
trace of alpha times of A1 is also 0. So is this a subspace or not?
Yes.
Yes.
But
So this, yeah.
like okay, I will think and ask them.
Okay. So now if this is a subspace, can you tell me the dimension?
2.
No.
1.
See, first of all, whenever you are given a question, you are doing math. So try to write down whatever is given, try to write down it explicitly. So you are having matrices A, B, C, D, where A equals C is 0. Okay. So it means you have D is equal to minus A. So it means you are having this set A, B, C, minus.
Minus A.
So now tell me.
3.
Yeah.
3.
Right? You know now how to find the basis also. Right? Okay. Suppose the trace is some non-zero number, then what happens?
Then it cannot be a subspace.
Then it cannot be a subspace, right? Because suppose it is, let us say 1. Then trace of A1 is 1, trace of A2 is 1, then trace of A1 plus A2 is not 1, right? So that cannot be a subspace. When trace of A is 0, this is a subspace. All right? Okay. So whenever you ask to find this, first of all, you should check whether it is a subspace. Suppose if it is asked, first check this and then do the basis part. Okay, dimension or basis, whatever. Okay, clear?
Okay.
Yes, ma'am. Yes, ma'am.
All right. So the next question, find the dimension of the vector space V is equal to O. Here you have for the 3 by 3 case. So already we have seen it for 2 by 2 case. So now it is very easy to tell 3 by 3 case. Tell me what is the dimension?
8.
So yeah, it should be
8.
yes. Dimension of V should be 8, right? Because here you are going to have A, B, C, D, E, F, G, H, I, where A plus E plus I is 0. And the elements are from R. So now this means what? You can write the same set as A, B, C, D, E, F, G, H, and then
minus a minus e.
-a -i.
right?
Yeah.
So the remaining entries from R. So this is a set. So you know that the dimension is 8. All right. Okay. Let V be a vector space which is defined as follows. So V is set of all x comma y comma z comma w such that x plus y is equal to z plus w and x plus w is equal to y plus z. So now we are in R4, but you know the technique already. We have seen a similar thing in R3. Now you are in R4. So nothing is going to change. You are going to follow the same procedure here. Shall we do? Right?
Yes, ma'am.
Okay. So here you see that now you have x plus y is equal to z plus w. So this is the first equation. And the second equation here is x plus w is equal to y plus z. Okay, so the first equation from that, let's say we can write w is equal to x plus y minus z. Right? So now let us write the value of z in, value of w here in the second equation. So here you have x plus y minus z, which is equal to y plus z. So now what happens? 2x and then y minus z you have. Let's bring it to the other side. So y plus z minus y minus z. So what is that you will have?
2z.
You have 2z, right? So you have 2x equal to 2z. So you have x is equal to
Z.
z. Okay. So now let us substitute x is equal to z in this equation. So what will you get?
W is equal to y.
W is equal to y. Okay. So now let's try to rewrite the given vector space. Set of all, you have x and y. And instead of z, what can we write?
X,
X. And instead of w, what can we write?
Y.
Y.
Y. So now can you tell what can be the dimension?
2.
2.
And what is the basis? X times of
1 0 1
1
0
0
0.
1
and
0
then y times of
5 times of 0 1
0
0
0
1
1 0
0.
1.
okay. So now you know a basis for V. So these two will form a, these two vectors will form a basis for V. Right? Okay, is this clear? How did we find a basis? Is this clear? We just solved the system of equations given here and we just wrote the solution here, removed the variables and got the vectors. Okay, clear?
Yes, ma'am.
Okay, fine. Okay, so we are
Ma'am, one
almost,
question, ma'am.
yeah.
Ma'am, suppose V1, V2, and V3 are the bases of a vector space R3. So if we add, we say like V1 plus V2 and V1 minus, will it be a basis of R?
So that was one of the problem I gave us a homework in last session, right?
I tried, but not getting the answer.
Okay, so maybe after we finish this problem, we are going to complete this session a little earlier, I guess. We will do at the end, okay?
Okay.
Fine.
Ma'am, before starting the run, I have a doubt.
Yeah.
So, can we, like, if we have a matrix, can we just flatten it and like write it as a vector and then try to check for the linear dependence or something like that if we are provided with few
Yes, you can do that. Yes, you can do that. But don't miss any entries. Okay. Sometimes what people do is that they write all the variables, whatever is given. Suppose there is a 0, they forget that there is one entry there. That is the problem of writing that as a vector. So
and
you can do that. Whatever you are asking, you can do. Yes.
and order of flattening also be same for all the matrices. Is it true? Like
So
the way we are flattening it, like the first row is the first three variables, and the second row is the next three variables, and third row is next three variables, and fourth.
patterning means, I thought you are saying something like this. Suppose let us say you are having something like this. So 2 by 2 case A, B, C, D, and then you have another maybe A1, B1, C1, D1. So instead of considering them as matrices like this, you want to consider
Yes,
them
yes, yes,
like
yes,
this, right?
yes. Yeah,
So you are considering them as vectors from R4 and checking linear independence, right? Yeah,
yeah.
it's
So in first matrix I have write A, B, C, D, and then second matrix I cannot write A, C,
no, no,
A1, C,
that
B.
that is incorrect. And
Yeah,
also
okay,
you have to be careful that the addition given is the usual addition. Otherwise, it is not going to work.
okay.
Fine. Okay.
Yes, ma'am.
Okay. Okay. So the next topic is the rank of a matrix. Okay. So far we have seen that. So given a set of vectors, how to identify uh, the number of linearly independent vectors, and using the linearly independent vectors and also by spanning this set, we formed a vector space. And also if we have a vector space, we saw how to find a basis. Now the rank of a matrix is something on the same line. So we saw the concept of dimension. Rank is also something similar to that. Okay, fine. Let A be an m by n matrix. The rank of the matrix A is the number of linearly independent columns of A. Okay, so rank of a matrix is nothing but the number of linearly independent columns of A. So the subspace spanned by the columns of A is the column space of A. Okay. So what is the subspace spanned by the column of A called? It is called the column space. And that dimension of the column space is the column rank. So here column space is a subspace of which space, can you tell? So you are considering the columns of A. So columns of A will form a subspace of which space?
The whole vector space.
Okay, so let me give an example. So you have 1, minus 2, 3, 1, 0, 1. Now these two vectors are from which space? The columns of A are from, let's say this is C1, this is C2. C1 and C2 are vectors from
R3,
R3.
R3, right? So this is, what is the size of this matrix?
3 cross 2.
Size 3 cross 2.
3 cross 2.
3 cross 2.
Now answer my question. The column space of A is a subspace of A is an m by n matrix. So the column space of A is a subspace of
R by n.
M.
R power n.
M, right? Okay. So on the dimension, so the column space of A will always have dimension less than or equal to M. Okay, fine. So the dimension of the column space is the column rank of A. Okay, so the dimension of this space we call as the column rank of A. Similarly, the subspace spanned by the rows of A is called the row space of A, and row space is a subspace of
R2.
After
R2.
R power n.
Rn.
n.
Rn, right?
Rn.
In general, Rn.
Rn.
Yes, sir.
So the dimension of the row space is called
Rn.
row rank, and the row rank is always
Less
less
than
than or
equal
equal to
n.
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 This is less than or equal to m, and this is less than or equal to n. So now it is a fact that we are not looking at the proof here, but anyway, it is a fact that row rank of A is same as the column rank of A is same as the number of linearly independent columns of A, the rank of A. Okay, row rank, column rank, and rank all are same. So sometimes it is easier to find what is the column rank. Sometimes it is easier to find the row rank. That is why we are using all the definitions here. Okay,
Okay.
fine. So
Ma'am,
yeah.
for a matrix, ma'am, I was trying to find this row rank and column rank, but I
Mm.
got confused. Like while writing the vectors, should I take the vectors in column when I'm taking this column rank, because we will have to perform this column operation on that.
See, when you are looking at the column rank, you are going to look at the number of linearly independent columns. When you are looking at the row rank, you are going to look at the number of linearly independent rows. That's all.
Ma'am,
Okay.
which operation, ma'am, we will perform while this finding this column rank? Column operation.
Okay, you are talking about REF form. Okay. So usually when you are looking at a matrix and you are doing the REF, you look at the number of non-zero rows. That's all is a technique to find the rank of a matrix.
Yes.
Okay. Okay, so from the fact given here, what do you people observe? It is given that column rank is less than or equal to m, row rank is less than or equal to n, and column rank and row rank are same. So what is that you can say in general? I have given this fact later also, but you should be able to observe it now.
Which of these two is
Minimum of
less? A smaller number, the rank will be equal to that number.
Yes. So it should be less than or equal to minimum of
M comma n.
m comma n. Okay, so this is also a fact which I have maybe stated later also. Okay. Okay, so now we are going to find the column space of A. So now what is the column space of A? Is the span
3.
of
Columns. Means
1 minus 1, 4, 2, 0 minus 2, 3 minus 1, 2. See, only the ranks are same. The spaces are not the same. Please remember that. Only the ranks are same. The spaces are not same. Column space and row space need not be same. Remember that. Okay. So column space of A is the span of all the columns. And what about the basis for the column space of A? So how do you find a basis here?
By echelon form.
Yes. So we
Reduce.
have to do the echelon form, right? So have we done this problem already? No, right?
No, no.
No, ma'am.
Okay. So how are we going to find the basis for this vectors? Can anyone tell? We are going to find the
Third,
REF.
REF.
REF form.
REF form.
Yes. So you find the REF form and then write the columns corresponding to the pivot elements. So can anyone straightforwardly can
Yeah.
find any linear combination?
The third vector is a combination of the first and the second.
Yes. So V1 plus V2 in fact, right?
Yeah. Yeah.
Yes,
V3
ma'am.
is V1 plus V2. So what are the basis vectors here? We can write V1 and
V2, yeah.
V2. Okay. So what is the column rank of A?
2.
Okay. And what is the row space of A here? So it is the span of 4 minus 2, or maybe I'll start with the first vector, which is 1, 2, 3, right? 1, 2, 3, and then you have minus 1, 0, minus 1, and then you have
4 minus 2 and 2.
okay, and here you have the following linear combination. The third vector is can be written in this way. So you can say that these two vectors, maybe this I call as R1 and R2. So R1 and R2 will form a basis for the row space. So what is the row rank of A?
2.
2.
2, right?
2.
Okay, so finding column rank and row rank, column space and row space, clear, right?
Yeah.
Yeah.
Okay.
Yes, ma'am.
So in general, how do you calculate the rank? So these are the steps to calculate rank. You find the row echelon form. Rank of A is the number of non-zero rows in the row echelon form. Okay. So elementary row operations do not affect the number of linearly independent rows. Yeah, this is what you should always remember. Okay. Okay. So now you are having this problem here. So the first step to find the row echelon form here is what? How will you do? R3.
Minus 4R1.
4.
4R1.
Okay. So what is that you are getting? 0.
Minus 10.
Minus 10.
Here minus 8, minus 2, so
Oh,
minus 10. And then here minus 12
Minus
plus
10.
2, again minus 10.
Minus 10.
Okay. What about the next step?
Take common minus 10.
Yes, that we can do. Maybe we'll do first for R2.
R2 plus R3. R1, sorry.
R2
R2
plus
plus
R1.
R1.
R2 plus R1.
So you get 0, 2, 2. And then here 0, R3 I can do. R1 minus 1 by 10. R3. So 1, 1.
1, 1.
So next step here is you do.
R2 is twice.
R2
R2 by 2,
twice
2.
of R3.
And this will become 0. Right? So you got the row echelon form now. So how many number of non-zero rows you have?
2.
2.
2.
Number of non-zero rows is 2. So rank is 2. So rank of A is 2. So we already have found the row rank and column rank, and we saw that they are 2. So this also is 2, which is matching. Okay, fine. Okay.
Ma'am, one question, ma'am. Can you please go? And suppose if you are interested in finding the column rank using this method, and you use this row echelon form or ma'am column echelon form, how are you going to do this operation?
For finding the column rank.
Yes, ma'am, using this method.
See, for finding the column rank, you can use either row echelon form or column or row. That does not matter. Finally, in row echelon form, how many non-zero rows you are having, that is going to give you the answer.
No. In column echelon form, ma'am, we will check the number of non-zero.
You use row operations or column operation. It's not going to change the answer I'm saying. Okay.
Can also use a column operation while finding the rank.
Yes.
So in that case, we will check the non-zero columns.
Non-zero rows.
I
rows
think
only, right?
when we form the matrix, then the column will be written as the rows, so that will give again the third row as 0. Means like we
Yeah.
can set the matrix like another form of like row and column.
The final
asking to
thing, you
transfer
are
the
going to have REF form. So in REF form, you are going to calculate the number of non-zero rows only. Okay.
Yes, ma'am. Okay.
Fine.
Ma'am, how is dimension different from rank?
How is?
Dimension different from rank.
Okay, fine. So now, what is the dimension here? We are talking about dimension of the column space is the rank of A. So we are considering the dimension of this particular space. Okay, or you can say the dimension of this space, the row space or the column space. So that dimension is the rank. Okay, fine.
Okay, ma'am. Yes,
Fine.
ma'am.
Okay, so now, okay, so here is the problem. Find the value of A if the rank of the matrix is 2. So if the rank of the matrix is 2, what is the fact you know? What is the what are the facts the rank of a matrix can tell? First of all,
Our
tell me
row 3
that.
will be 0.
Yes.
So
Its
suppose you
determinant
are
is
having an
0.
n by n matrix,
You
okay?
can say its determinant is 0 because it is a 3 by 3 matrix.
Yes. So rank of A is equal to n if and only if determinant of A is non-zero, and it is strictly less than n, means you can say that determinant of A is equal to 0. This
0.
property we have seen it in terms of linearly independent columns or rows. Remember? So if the columns are all linearly independent, then you will see that the determinant is non-zero. So the rank is nothing but the number of linearly independent columns, and hence the same property holds here. Okay? Fine? Okay. So find the value of A if the rank of the matrix is 2. So here we know that since the rank is 2, what should be the determinant?
0.
Okay, so now calculate the determinant of this matrix. 2 times of
A, ma'am.
A minus 6.
A minus 6
yes,
plus 1 times of
1 times or 3 times. Okay, you are expanding in this way.
yeah, yes, 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 yes.
Okay, then I have to rewrite it.
2, 2.
Ma'am.
Then I have to rewrite this term as well, right?
No, ma'am, that will remain
Ma'am,
same.
Oh, okay,
try
fine.
2A, ma'am.
Go that way only. Yeah.
And then minus 1 times of
Uh, plus 1. Plus 1 times.
plus 1 time of,
Uh, 6 minus 4.
yeah. So what is the answer?
2 minus 12.
So 2a minus 10 is 0.
0.
So if 2a minus 10 is 0, what is a?
5.
5. Suppose the rank is 1, then what will happen to the value of a?
Then we cannot comment on it, I guess.
Suppose the rank is 1, the determinant is still 0, right?
Oh, yes, yes, sorry, rank is 1.
Yeah, so if the rank is 1 also, nothing is going to change. You still are going to use the same technique, determinant 0, and do the same procedure.
से ने बोला वो स्टैपलेस प्रा दे रही है.
Okay, so if you are not talking here, please mute yourself.
वो दे रही है उनके पास पड़ी है.
Okay. All right. Okay, so the next question here. Choose the set of correct options from the following. Row rank and column rank of a matrix is always the same.
No.
Yes, ma'am.
Yes, right? Yeah.
Yes.
The
Yes,
rank of
ma'am.
a 0 matrix is always 0.
Yeah.
Yes.
Because the determinant will be 0.
Yeah. Not because the determinant is 0, because there are no linearly independent rows. Well, we are counting the number of linearly rows or columns, right? 0 matrix means no linearly independent rows or columns. So
All
that is
rows are 0.
not because of determinant. We don't even know whether it is a square matrix. They have just given rank of a 0 matrix. Okay,
Because
be
all
careful.
rows are 0 in the
All rows are 0.
Okay, any doubt you are asking? What? Okay,
No,
there
no,
are.
I was just
Yeah.
commenting, ma'am, that all rows will be 0.
Okay, yeah. So the rank of a matrix, all of whose entries are the same non-zero real number, must be 1. True or not?
True.
True.
Right?
True.
For example, if you are having A, right? So what is the rank of the matrix? So the row echelon form will be just 1, 0, 0, 0, right?
Yes.
So in that case,
And
you
1,
can,
1.
sorry, 1, 1, 0, 0. So in that case, you know that the rank of the matrix is going to be 1. Okay. What is the rank of an n by n identity matrix?
3. Oh, sorry, N.
N. So this
We cannot say
n. Okay. Okay. What is the rank of a non-zero scalar matrix?
3.
I just
No,
asked
it
what is
depends
the
on the.
rank a non-zero
It
scalar
depends.
matrix. It should
It
be
depends
the
on the dimension
rank
only.
of the matrix. So whatever is the n, that is the answer. Okay, fine. Okay.
Could you please explain the option 3 again?
Option 3. Okay, so here you are, suppose I'm taking a 2 by 2 matrix. Okay, so all the entries are same. If all the entries are same, row echelon form, the last row will become 0.
Okay.
Okay, so you forget about 2 by 2. You take any n by n matrix where all the rows are same. You can make all the last n minus 1 rows 0, right? But in the row reduction,
We can take that top row also can be a 0, right? Then
that
we
is why
cannot
they
say
have
that rank will
mentioned
be.
non-zero real number. It is mentioned it is non-zero. So how the first row can be 0?
Okay, okay, okay.
Okay, got it?
Got it.
Ma'am, can we say that the rank of a column matrix is always 1?
The rank of a column matrix, yes, that is also 1 here.
Or similarly, rank of a row matrix is also 1.
Okay, you are asking about a column matrix. Yes, yes. So the
Yes.
rank of a non-zero column matrix
Column
is 1.
matrix is 1.
Yes, yes. The non
Non-zero row matrix is also 1.
yes. Non-zero, if it is non-zero, then 1, yeah. So what he was asking is that suppose you are having a, let us say, m by 1 matrix, or you are having a 1 by n matrix, and it is non-zero, then the rank of those matrices are 0. Sorry, 1.
Ma'am, I have read that rank of a zero matrix sometimes may be undefined.
See, it depends on the way we are defining. Rank of a 0 matrix, will have it as 0 only. Let's not undefine it. For our case, we can have it to be 0 itself. Okay.
Ma'am, can you explain option 4 again?
Okay. So for option 4, the 2 by 2 identity matrix, let us consider. So is this in REF form already?
Yeah.
So how many number of non-zero rows do you see?
2.
So what is the rank of this matrix?
Okay, 2.
So the same holds for any n by n matrix also. The rank of an n by n identity matrix is n. Okay?
Yeah.
Okay, fine. So this first fact I have already mentioned to you. The second one, you should know rank of AB is less than or equal to minimum of rank of A and rank of B. So the product of two matrix, if you are having, then the rank of the product is less than or equal to minimum of the rank of first and the rank of second. Okay, so the first fact I already have explained. Second, it's a bit lengthier. It's enough if you know just the fact. Okay. Okay, so here find the rank of this matrix using row echelon form. So I have assigned it as a homework because just doing row echelon form here. But can you just tell what is the maximum value of rank for this matrix? So rank of A is less than or equal to
3.
3.
right? Because this is a 3 cross 4 matrix, and using this property, we can say that rank of A is less than or equal to 3. And what is the exact rank? Find it using row echelon form. This I have given as a homework. All right. Okay.
Okay.
Fine.
Ma'am, can you again explain the identity matrix one? Can you scroll up?
Yeah. See, all
Yes.
identity matrix are in fact in RREF form, right?
Ma'am, I can claim that using just this 1001 and scalar multiplication, I can always reach all of the identity matrix. So shouldn't it be 1 always?
What?
No, no. Number of non-zero rows, bro. What are you talking?
I don't understand that. See,
Let's-
rank, the definition of rank, let us call this I2. So the rank of any matrix here, we are talking about rank of IN, is the number of non-zero rows. Definition is this: non-zero rows in the REF form of IN. But REF of IN is IN itself. So in has n rows, and so the answer is n.
Oh, ma'am,
What's the confusion here?
so I was looking at from a basis point of view. So if we were to find a basis of this kind of matrix, it will have one.
Hold on. We don't find a basis for a matrix. We find a basis for a vector space.
Okay, yeah, makes sense.
Okay, fine. Okay, maybe some of you can work on this problem while I have a 5 minutes break. Okay, please work on this. I'll come back in 5 minutes.
Okay, ma'am.
Okay, so did you find the rank? It's 3, right?
3. Yeah, 3.
See, ma'am.
Okay. So the rank of A is 3. All right. Consider the following upper triangular matrix. A is equal to ABC 0DE 00F to choose the correct options. Okay, so what is the type of this matrix? Can you tell? This is a,
Upper triangular.
yes, this is the upper triangular matrix. So it is given if F is equal to 0, then the rank of the matrix must be less than or equal to 2.
True.
2, right? Okay. If F is equal to 0, then the rank of the matrix must be exactly 2.
Depends upon A, B, C, D, E.
Yes, depends upon the other values. So we cannot guarantee this, right?
Yes.
If A, B, C, D, E, F are all non-zero, then the rank of the matrix must be 3.
True.
Yes.
No,
True.
ma'am. It can be less.
It can be less. See, when all of them are non-zero, what happens to the REF? This you have to just divide by 1 by F then, correct? Yeah.
Yes.
And this you will divide by 1 by D. And this you will divide by 1 by A. So you have 1, 1, 1 here. You got the REF form with 3 non-zero rows. So the rank must be exactly 3, right? Okay?
Yes, ma'am. Yes, sir.
Yeah. If A, D, F are non-zero, then the rank of the matrix must be 3.
True.
True or false?
True.
Correct.
True.
True. True.
For the same reason. All right. Okay. What is the rank of this matrix? So how do you find the rank of this matrix? So here you have to do the REF only. So in the REF, you are going to just do some uh, operations. Just you are going to do instead of numbers, you are having variables here. That's all is the difference. So we are going to find the REF. So to find the REF, what is the first step we can do? Can you tell?
R2 minus A times R1
R2 equals to R2 minus A times of R1. And similarly, we can do R3.
minus A
A
square.
square times
A
of
square.
R.
Yes.
So what is the resulting matrix?
Oh, yeah.
B minus A.
A, C minus A.
Minus A.
Okay. Here
0. B
B
square minus
square
A.
minus
Below
A
B square
square.
minus A square, C square minus A square.
yeah. Okay. What can be the next step?
R3 divided by B square minus A square.
How do you know B square minus A square is non-zero?
Hmm, how do I know? A, B, C are distinct non-zero integers. Then distinct, so their square will be also distinct, and then it will be always non-zero. Their difference.
See, minus 1 and 1, they are distinct numbers, yes or no?
Oh yeah. Oh yes, yes, yes,
But
yes.
their squares are not distinct, right?
Yeah.
Okay. So here one property you can use. Here you have B square minus A squared and here you have B minus A. What is the relationship between them?
And we can do
There is a
R3 divided by
multiple of
R2.
R3
B
divided by
minus
R2. Can we do, ma'am?
B minus A into B plus A.
No need for any division if you know this formula. Now I have given the formula. Now can you tell what is the step we need to do?
R3 equals to
Yeah.
R3 minus B plus A
Yeah.
R2.
Correct. So if you do this, this term will become 0 and here you will have C square minus A square minus B plus A times of C minus A. Okay. So now you have to justify that this term is non-zero. First of all, let's simplify this term. So you have C square minus A square. And then when you do the multiplication, you have minus
BC
BC plus
BC
BA.
plus A, or shall we maybe write the C plus A, C minus A formula, and that may be easier, I guess. C plus A
Yes,
into C minus A minus B plus A into C minus A. So I have rewritten C squared minus A squared minus B plus A into C minus A in this way. Now I can take C minus A commonly.
C minus B under
C plus A minus B minus A. So what's the answer? C
C
minus
minus A into C minus B.
C minus B. And these two are non-zero. Do you agree? Because they are
Yes,
distinct.
ma'am.
So you know that this term is non-zero. If this term is non-zero, can we divide it by this number?
Yes, ma'am.
Yes, ma'am.
So you see that 1, 1, 1, and the last row will become 0, 0, 1. What can we do for R2?
B minus A divided by B.
Yeah, you can do R2 by B minus A, because you know that B minus A is non-zero. So you will have 0, 1, C minus A by B minus A. Now can you tell me what is the rank of this matrix?
3.
Right.
You have 3 non-zero rows. So what is the rank of the matrix?
3.
3. Is this clear?
Yes, ma'am.
Okay, fine. All right. So we are almost at the end. So I will just ask one matrix problem here. So do you remember, did I introduce the term skew symmetric matrices?
Yes, ma'am.
So what are skew symmetric matrices?
For which A is
It
equal
has to
to negative
Minus A
or
transpose.
yes,
A transpose is minus
minus it.
A. A is minus A transpose. Anyway, it's fine. Okay, such matrices are called skew symmetric matrices. Okay, suppose I am considering a 2 by 2 skew symmetric matrix. Okay. Now, what is the transpose of this matrix?
ABC.
ACBD.
ACBD.
Now, it is given that it is equal to minus A. So, minus A, minus B, minus C, minus D. So, what is that you get?
Yes. C is equal to minus B and A and D are
Minus
zero.
common and then AC.
So
A is equal to minus A, B is equal to minus
B
C,
equals to minus C.
D equal to
D
minus D.
equals to
So,
minus D.
what can you say about A and D?
0.
There is 0.
And B is minus C. So, the set of all skew symmetric matrices can be written as 0,
0
B,
minus, yeah, minus B and
Minus
0.
B.
and 0. Right? All right. So, can you tell, is this a subspace of M2 of R? Is this a subspace of M2 of R?
Yes,
Yes, right? It's a
yes,
subspace.
Yes, ma'am.
yes.
Okay. Okay. What is the dimension of this subspace now?
1, 1,
1.
1.
2.
1 or 2?
1.
1, ma'am.
1, ma'am.
1, right? And the basis is given by 0, 1, minus 1,
Minus 1.
Minus 1, 0.
0. Okay, fine. So I
Ma'am.
tell you, try to do the same for find the dimension of 3 by 3 skew symmetric matrices. Do this as a homework, okay?
Okay, ma'am.
Could you please explain again how that A and D, like you got as 0?
Because A minus A is 0. So A is equal to minus A. Any number equal to its negation means it's 0. Or you can also see it as 2 times of A is 0. So A is 0.
Okay, okay. Got it.
Okay. Fine.
Yeah.
I have covered almost all the important examples needed for you. So now you can ask your doubts.
Ma'am, could you please like come on building of that spanning set? How to build one? We have
From
like
the
3 or 4 steps, right?
building
Yes,
of
ma'am.
spanning
There
set
were
of which system spanning set?
I also have the same doubt,
from
ma'am.
building of the
Building of the
spanning set.
planning set, because there is
There
one
were
property, ma'am,
yeah.
where it is clearly mentioned in the professor in the video lecture only, where
Okay.
it is written that every linearly independent set can be extended to form a basis. And
Yes. Yes, true.
yeah, so
Yes.
like, ma'am, um, so
Should I
how
open my
how to
previous week session? Previous week's PDF? Previous session PDF?
Previous sessions, ma'am. Yes, ma'am.
Yeah.
Yeah.
If you
yeah.
can please.
Yeah, I'll do that. Hmm. So which one we are talking about?
We had
So
few steps here. This is.
this one?
Yes, yes,
Uh,
ma'am. This one.
Yes, ma'am.
This one.
Okay, so what is your doubt here?
Actually, I'm not able to build one. That's why.
Yes, ma'am. Exactly. That
Okay,
is
so
the
here
problem.
you are having, okay, let's do it step by step. So step 1, you are having the vector. So let's call this set as S1, which is 1, 2, and 3. Okay. Now you are going to add another vector to this, which is not a multiple of this. Okay. So you can take any vector which is not a multiple of this. So I can take a simple vector which is maybe 1, 0, 1, 1, 0, 0. Okay. So now step 2, I'm adding a simple vector 1, 2, 3, 1, 0, 0. Are they linearly independent? They are not multiples of each other, right? So they are
Yes,
linearly
ma'am.
independent. Okay. So now step 3, I have to find a vector which is outside the span of this. Okay. So it should not be a linear combination of this. So what is a typical linear combination of this? Can you tell? Alpha times of 1, 2, 3 plus
Plus beta times of
Yeah.
100.
100.
right? So it should be alpha, 2 alpha, 3 alpha plus, here the first term is alpha plus beta. Okay, so what do you observe? The second coordinate and third coordinate are multiples of alpha. Okay, so
Yeah.
if you break this rule, then that cannot be inside this linear combination. That is how you are going to choose another vector. Okay, fine. So
Could you
suppose,
comment that again?
see, here you are having multiples of alpha, 2 times of alpha, 3 times of alpha. So whatever number you are having, it is 2 times of one number, and then the third coordinate is 3 times of the same number. So
Yeah.
if you are able to choose numbers here such that you cannot write them as 2 alpha and 3 alpha, then you are done.
Yeah, got it.
Got it?
Yeah, yeah,
Yes,
got it.
ma'am.
So can you suggest some vector then? Can we choose first
Two,
one as 0?
0,
Yeah, 0 and then
5,
5.
7.
Okay.
0.
Okay. So
Then
if
can
5 is equal to 2
how do
alpha
we get
and
this?
7 is equal to 2 alpha, 7 is
3
equal to 2
alpha.
alpha, will you
Yeah,
get any
3 alpha.
solution? Alpha is 5 by
No,
2
no.
and alpha is 7 by 3. So it's not matching. So
No.
it's not clashing with this problem. So 0, comma 5, comma 7 does not
Okay.
belong to span of S2. Correct?
Yeah.
So you have got another vector. So S3 you have got, that's all. Done? So So always choose a simpler vector so that it is easier for calculation. Here, if you choose some complicated vector, then this linear combination also will get complicated. Okay.
Yes, ma'am.
Okay, ma'am.
Could you please
So,
give
ma'am,
some
we
idea
can
how
make.
we can select the vector in the steps two, like that?
Can you please ask
Because,
your question louder?
ma'am, could you please explain that how we can choose a random vector in step two?
See, step 2, you just have to choose a vector which is not a multiple of the first vector. That's all. Any vector which is not a multiple of the first vector. I want to
Whether we can choose that having some zeros, that may be easy, right?
yes, yes.
Yeah.
So for making
Zero
it
and
easier,
one
we are putting as many
only
zeros
then
as
is
possible.
easy.
That's all.
Yes, ma'am. Got you.
Okay.
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 Okay. Yeah. Any questions now?
Ma'am,
Could
can
you
we
show
start?
this?
Can we start with an empty set in this?
Yes. Empty set also. If you start,
So
that
the
is
steps
even
will
more
be
easier
changed.
actually. It is even more easier actually. So I will start with 100 and then I will
Hmm.
get a set very easily. Okay.
Ma'am,
So
what
there will
do
be
you
only
mean by
two.
that?
There will not be two. There will be again anyway three vectors. You are constructing a spanning set for R3, right?
Yes, ma'am.
Then always you need three
So, ma'am,
linearly independent
if we're
vectors.
gonna start with zero, then
Mm.
what will be the steps? The steps will be same or it will be different
Yes,
a
the
bit?
steps. One extra step will be there. That's all. So first vector is zero vector. Then you have a non-zero vector, and then the other two steps which we did here. So just one extra step here. That's all.
Oh, first we have to assume any other vector, right?
Yeah, yeah,
Any vector,
yeah,
and then go accordingly.
yeah,
Okay, ma'am, got it.
Ma'am, ma'am,
yeah.
this zero vector is linearly dependent in itself, right? So how can we start with the dependent?
See, this is kind of a void step. So usually you do, and I don't know, in programming you do some void step in the first, right? Something like that you can consider. This is not even required. You can start with any non-zero vector. In fact, you can
Yeah,
just
like
this.
what's the use of like taking this
Yeah,
extra
yeah. There
vector?
is no need for. See, this is kind of the zero step. They wanted to start with zero step. That's why they have starting with an empty set. They are showing the steps, but it's not required. You can start with a non-zero vector. Okay. So here
Yeah.
the steps are given from starting from the scratch. That's what they are showing here. Starting from nothing. That is what they are showing.
Because
That
It is
because ma'am,
similar
if
like
we,
building a structure of array and then more proceeding with that.
whatever
no,
comparisons you
ma'am,
can think of, that is up to you. Yeah.
this will then violate the entire things that we have learned because the superset of this dependence set will always be a dependent. And if we apply that found thing, then any vector if we add, it has to be dependent. Are you understanding what I'm trying to say, ma'am?
See here, S1 they are writing as S naught union 110. So here S naught is an empty set, so there is nothing to comment about it as dependent or linearly dependent. So we are not violating
Yes.
anything. We are not talking about span of S naught. We are talking about S naught only here. So we are not violating anything.
Okay, ma'am.
So 000, this element is in all the spans, right?
In all,
Like if I taking a span of R3, then 000 will be there. If
yes, span as in any span of any set, 000 is. I mean the origin is going to be there, or the zero vector is going to be there.
yes, yes, and we can also say like because every line in like if we take one vector and we say the line passing through origin, so
Mm.
that origin is also included. So we can say that yeah, 000 is will be there.
Yeah, so it's just a step it is given. If you want to just skip it, yeah, you can skip it. Or if you want to have it also, it's up to you. It's not a very important step here, step one.
Ah, ma'am, I got it.
Okay.
We don't even check for this dependence and independence for this span.
Yeah, yeah.
It's for basis, right?
For basis, we need to check dependence
Correct.
and independence is required. But here, this step, they are just showing that we are starting from an empty set. That's all.
Yeah, I got it. Thank you.
Okay. Okay. So, any other questions from today's session? Any questions?
Not
That
from the
question that you gave for assignment.
Ma'am, that maximum linear independent, what was that, ma'am? A bit of insight on that.
Maximum linearly independent. Which one?
Ma'am, it was in the building one.
Definition of basis, I think.
Yeah,
Yeah.
that's
Maximal
minimal
linear.
spanning means and
Oh, the
the
equivalent
maximal linear.
conditions you are asking. Okay,
Yeah,
the
it's the
equivalent
third and
conditions you
fourth
Ma'am,
are
there
asking.
condition.
was it has some meaning, and I was just a bit of
This one, right?
Yeah,
yes,
could you
ma'am.
explain
Yes,
like
yes.
proof? It's given a
Yes.
proof is also given.
Yes. See, whatever you suppose, let us say you are having a set V1, V2, Vn, Vk. Okay. So now you know that suppose this is a linearly independent set. Okay. Now I am going to add another vector to this set. Okay. Now, if this set, whatever vector you add, any vector, any non-zero vector, of course. Okay. If I'm adding any non-zero vector here, okay, to this set, then this set, if it becomes linearly dependent, then this set is called maximal linearly independent set. Okay, this is the maximum size for this set to be linearly independent. If you add another vector, any vector to this, then it will always be linearly dependent. Such a set is called maximal linearly independent set. Do you understand?
So, ma'am, what's the use of this condition here, ma'am? That's the question.
Can we find out what is the maximal, I mean, the size of the maximal linearly independent set?
See, what is the purpose here is that, see, for example, suppose you know that you are having a plane, right? So suppose you are having a plane and your V is your plane. Now you are having two linearly independent vectors. Okay, some linearly independent vectors, let's say V1 and V2. Now you know that for a plane, this is a maximal linearly independent set, right? For a plane, there cannot be more than three vectors which are linearly, more than two vectors which are linearly independent. Yes or no?
Yes, ma'am.
So in that case, this will form a basis, correct?
Yes, ma'am.
Yes, that is what it is saying here. If you know that a set is maximal linearly independent, then that is the basis. That is what they are saying. Okay, fine.
Mm, yes, ma'am. A bit.
Okay. So the same thing they are saying about minimal spanning set as well. Suppose you are having V1, V2, Vk. Okay, and you are having span of this set is equal to V. Now suppose you are removing any one vector from this. Any one vector, any I. Okay, I is between 1 to k. If I am removing this, then span of this set is not equal to V. Then this is called a
Mm,
minimal spanning set.
yes, ma'am.
Okay, fine.
Mm, yes, ma'am. That's easy one.
Okay.
Okay.
Okay. Any other questions? Someone was asking a question. I guess this was the question, right?
Yes, this was the question. Yes.
Yeah. So I have explained one part actually already here. So you are given that V1, V2, V3 forms a basis. So basis means you know that they are linearly independent. And you know that for R3, any basis will have three elements. So you are having three elements in every set. So you are going to check whether they are linearly independent. So that is the only condition you are going to check for all these sets. So the first set I have explained, alpha 1 V1, alpha 2 V2, alpha 3 V1 plus V3 equal to 0. If this is linearly independent, what it should imply?
It is, in the
The
basis.
coefficient should be 0.
Then the coefficients, yeah, they are
Yeah.
should calculate.
So now I'm going to rewrite this. I'm clubbing this first term and alpha 3 V1. So I'm having alpha 1 plus alpha 3 V1, alpha 2 V2, alpha 3 V3. Now I know that
No, I got
V1,
it, ma'am. Got it.
okay, got it.
Ma'am,
So
yes.
this is linearly independent. So the coefficients are 0. And from this we obtain the coefficients of the original set is 0.
Yes. Ma'am, so we
Okay.
will have to check for all the three options like this.
Yes, yes, yes. For
Okay.
other
Thank
options
you.
also you have to check the same way.
Got it. Thank you.
Okay. Any other questions?
No, ma'am.
Okay, then I hope
The
all
last
these
question which you
topics.
have asked.
Which one?
The last question which you have asked. Uh,
Last question in today's session.
In today's, yes, 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 in today's session.
This one.
This one.
This or this.
Not this one.
Okay, this one.
Yes.
So what's the doubt here?
This Q symmetric part, the second part.
Okay. What's the problem here?
You have asked about the is it a subspace or not?
Yes.
I didn't understand how it.
Okay, so you have to just pick randomly two vectors from this set. So let us call this W. So I am taking two vectors. W1 is maybe I will take A1 is 0, B1 minus B1 0, and A2 is 0, B2 minus B2 0. So these two are in W. What about A1 plus A2? Is that also in W? Yes, right?
Got it, ma'am. Got it. Got it.
Yeah. So similarly, scalar product also is there in W. So it is a subspace.
Ma'am, one question I had, it was from augmented matrix actually. So can I ask?
Okay. So is it about a specific problem?
No, oh no, ma'am. It was just a theory part. I just wanted to ask, ma'am, like, what is the condition that augmented matrix have infinite solution or unique solution? I was just confused about that.
Okay. So maybe that we are going to do in the revision session on Wednesday. So that time, maybe
Okay,
after
ma'am.
revising also, if you have doubt, you can ask. Okay.
Okay, ma'am. Okay, ma'am.
Fine. Okay. By the way, you are having revision sessions on Wednesday and Thursday, and the mock is already released. Have you all seen the mock?
Yes, ma'am.
Yes, ma'am.
Okay, so please work on the mock questions. You can discuss the mock solutions on Saturday TA session. Okay?
Okay, ma'am.
Okay, ma'am.
Okay.
Okay then. So see you again on the revision sessions. Bye.
Thank you so much.
Thank you, ma'am.
Thanks, ma'am. Good night, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am.
Yeah.
Thank you.